technology, and I see that there are a bunch of questions that have been saved up here. I'm in the middle of a big kind of history of science adventure right now, because I've been working on the second law of thermodynamics. I've been working on the science of that, the sort of future science of that. But I've been going back because some of the things I figured out about the future science of that don't really agree with the things that are part of the conventional wisdom about the second law. And so I've been interested in, well, where did that conventional wisdom come from? And so I've been digging backwards into the history of things. And I will say that I'm still in the 1600s, but it's been interesting what I have learned. I mean, I can share a few things. So once people had figured out what heat was, that heat was the microscopic motion of molecules, the second law got formulated very quickly, within 10 years, and in its pretty much its current basic form. But figuring out what heat was a long story. And so back in antiquity, Democritus, the Epicureans, they had this idea that the world was made of atoms, these indivisible things, atoms in the void. And they had kind of this notion that there were two kinds of things in the world, atoms and the void. And there were people who said, everything is just sort of a continuum, a plenum. And then there are people who talked about atoms. It's interesting that in our model of physics, we finally get to unify the notion of atoms and the notion of the void. Because in our model, the things that make up space are themselves atoms. There isn't just atoms embedded in this void of space. I also learned a thing recently about Descartes from the beginning of the 1600s. Descartes had this view of the world in which everything was made of not quite atoms, but these vortices, that the whole world was made up of all these little tiny vortices interacting with each other. And one of the things that Descartes believed is that you couldn't have distance in space without there being vortices in between those two places that there was distance between. In other words, that to have space be a thing that you'd have to go through, there have to be vortices there, that there couldn't just be an empty void there. And so that was that's interesting because that's very much what happens in our model of physics, that there isn't any distance between 2 points in space unless there are nodes in the hypergraph between one point and another. So this is actually turns out to be a rather, amusingly, it's sort of a Cartesian idea, even though the notion of coordinates that was another Cartesian Descartes idea is something that we eschew in our model on the grounds that what we're really dealing with is just these atoms of space, so to speak. But in any case, the thing that people thought about heat was they thought there were these different kinds of atoms, the air, water, another one, and fire, as well as quintessence. But fire, they thought there were fire atoms, and they thought, this is now with Democritus, 5th century BC, was thinking that that heat was the presence of a lot of fire atoms, and fire atoms were spheres, and spheres could kind of get through other things. And so this sort of heat was able to sort of slide between other pieces of the world, other pieces of matter, and could be so that something that was hot here could make something else hot here. So that was kind of their model, but they had a very strange sort of connection there because they also thought that the soul was made of fire atoms and that the soul was the ultimate seat of all motion, that in order for things to move, there had to be a soul that was ultimately moving those things. And so they had this kind of relationship between the soul, the notion of animals that could move, I think works better for warm-blooded animals, and the notion of heat as a thing that was a disembodied thing. So, that was kind of the version in antiquity, that heat is the motion of little tiny corpuscles of fire, little fire atoms through the other constituents of the world. Well, for 2,000 years, people didn't figure out anything better. And I've been looking at the alchemists and so on. The alchemists didn't even have a notion of gases. They knew about the air, but they didn't talk about gas as a thing distinct from air. And they knew that there were things like steam and so on. They knew there was carbonic gas, carbon dioxide, things like that. But they didn't really think of a thing that was this notion of a gas. And so I don't think the alchemists contributed anything to this. And then we get to the kind of early modern times we get to, for example, Galileo. And I just found a thing yesterday from 1623 from Galileo in which he's talking about heat. And he says, heat is the result of tiny corpuscles that transmit the heat. And he says, and when they get into us, then they excite our senses. The tiny corpuscles kind of are things that kind of we sense those corpuscles as they move through us. And he notes that when you have a glass thing, smells can't get out of the glass thing, but heat can. And so he says they must be very subtle atoms of heat to be able to escape the glass thing in a way that a smell cannot escape the glass thing. But, and he has a whole description, actually, he has an interesting description that the very smallest, he thinks that these sort of atoms, I don't think he calls them corpuscles, I think, of fire, although I need to look at the original Latin because I'm not sure exactly how. I was just looking at a translation, which is always a dangerous thing to do. Of course, it only works if you know the original language, and I know probably enough Latin to be able to tell whether the translation is iffy. And you have to understand that translating things from that period of time is a complicated matter, because the concepts that we have now, like the concept of a gas, didn't exist at that time, and so if you are going to translate a thing that Galileo said, or for example, the notion of an atom at the time of Galileo was different from the notion of atom today. So if you're going to translate something that Galileo wrote, it's complicated, whether you translate it into the terms of today, or whether you try and use somewhat more neutral terms, which are then harder to understand, that don't directly connect with the terms that we use today. But anyway, so Galileo has this thing where he says, maybe these fire corpuscles, when they're broken down, I couldn't really understand what he was saying, so I'm going to go look at the Latin and maybe I'll have a better luck there. When they get broken down enough, they are no longer caloric, they are no longer heat, they are instead light. And what that relationship in Galileo's mind is, I'm not quite sure. Now, it's interesting that Galileo has this this kind of really quite mechanistic view of heat. It's quite a clean description. I mean, it isn't quite right, but it's quite a clean description. Francis Bacon, same time, 1620-ish, has a whole thing about heat is motion, but it isn't really motion. Actually, Galileo makes a comment about this as well. He says that heat is somehow related to motion. It's related to motion of these microscopic things, but it isn't the same thing. When you move a piece of iron around, that doesn't make it hot. It's some other kind of motion that happens inside the iron. Now Bacon is a bit more abstract and talks about heat and motion are somehow the same thing and one can produce the other and so on, but it's all kind of vague. Galileo is much cleaner, much more sort of to the point, even though he doesn't quite get it right and he doesn't really know how it works, but it's much better presented, so to speak. Now, the thing I literally just, when I ran out of time last night, was studying was Robert Boyle. And Boyle, developed Boyle's law of 1666-ish time frame, that kind of time. A bunch of other people have been working on the notion that air is elastic, that air is something that, like a material, you can kind of crush it, and it behaves like a material. It also spreads out to fill a container. There have been a bunch of people who've done experiments around the same time. Robert Hooke was an assistant of Robert Boyle's. I'm always have kind of I don't know much about Robert Boyle, and I need to learn more about him, but I sort of have a soft spot for him for one reason, which is the high school that I went to, a place called Eton College that was founded in 1450 or so in England. For a while, I don't know if it's still true, but it listed on places like Wikipedia, scientists who went to Eton College. And for a while, there was Robert Boyle, and then there was me with 300 50-year gap or something, which I just thought was rather charming. I think there are others, and I think that's an inadequately filled in list. But that was gave me a kind of felt like I had a personal connection. Now I actually was just looking up Robert Boyle's life at Eton College, and it was definitely a little bit less organized than it was by my time, so to speak. But in any case, Robert Boyle, I believe, wrote about kind of well, actually, we should say something about how the idea of a gas emerged. So there's a guy, Jan van Helmont, who was a Dutch Flemish physician and philosopher. Those were combo occupations in those days. Was a physician who was very opposed to kind of the Hippocrates-Galen tradition of medicine, which had been this idea of these elements that were just like kind of the elements that everything was made of, and then that turned into the notion of humors, and I don't know, all of medicine from the Middle Ages and so on, and from antiquity. This notion of, that led to all of these bizarre medical sort of treatments, bleeding things and various kinds of fluids in us humans, putting more, getting less, all this kind of thing. And it was all about sort of the balance of these fluids. Of course, they had no idea that there were anything microscopic wasn't understood at that time. And I have to say, I'm a little bit sort of sobered to think of the medical treatments of today, how many of those will look like they were bloodletting type treatments. We will say of them, those were as silly as the bloodletting treatments of the 1600s were when, at some point in the future. But in any case, Van Helmont was a person who didn't really believe in the kind of approach to doctoring that had come from Galen and Hippocrates from antiquity, and was kind of fighting against that. And one of the things he did was he figured out something which I haven't yet understood very well about disease and gas, and the idea that you could breathe out a gas, that's carbon dioxide of some kind. It's a different kind of thing from what's in the air in general, and those types of things. And in fact, he coined the word gas. And there's a strange piece of etymology because the word chaos, chi alpha omicron sigma in Greek, is a word that has now been turned into kind of this notion of chaos and chaotic and randomness and so on. In Greek, I should say, why is this related to gas? Well, it's related to gas because Van Helmont basically was giving the Dutch rendering or the Flemish rendering of the word chaos, whatever your favorite pronunciation of ancient Greek, which we don't really know what it was, but anyway, that rendered into Dutch was gas. And that's where that term comes from. So gas is a term for chaos. So then the question you might ask is, well, what did chaos in ancient Greek actually mean? And what it meant was a void. It was the void in which, for example, the atoms of Democritus lived. In fact, I need to look up, unfortunately, very few of Democritus. I don't think any of Democritus's original writing has survived. I think people think Theophrastus, for example, who's mostly known for his botanical works. I think he talks about some of what Democritus said, and other people talk about Democritus and Leucippus and the other Epicureans. I don't know how much has survived, so I don't know whether one can read what the atoma, the indivisible atoma. Do I know my Greek? Tomo, I would guess, was the first person singular. I mean, to cut. And so an atom is something which cannot be cut. But I would like to know actually what the translation of void in Greek is. I presume it's the same word, chaos. And so that word means kind of a void, an empty space. Well, probably an empty space, unless you're Descartes, where the void is full of vortices. But and that it also had got this notion of kind of formless, primordial formlessness. And I think that's where in the English translation, things like, Genesis and the Bible has, things were without form. What is it? I'm now forgetting, but void and without form, so to speak. And this notion of sort of primordial chaos, which I think also existed in Greek mythology, was this notion of sort of a formless nothingness, sort of. And that was the thing that turned into the word for gas. So, okay, now we're in 1666, and I guess, do I know my history well enough? Is that the time when the English Civil War was in? No, that was the time of the plague. That was the time of, yeah. But anyway, so Boyle is hanging out with his sister, Catherine Jones, who seems to have been quite a contributor to his activities, and doing experiments on air, and trying to figure out what air is. Now, somewhere, because I found a bunch of quotes of this, Boyle talks about two theories for what air might be, two theories for what it might be made of. One, that it is a fixed array of corpuscles with little springy things between them. So it's kind of like a crystal of corpuscles with springs between them, which somehow expand out into the size of a container. That's theory number one. Theory number two is it's some kind of vortices that bump into each other, in a bit more like what Descartes was talking about. And Boyle, I gather, did not really have a preference between these two. But I need to find what he actually wrote. And unfortunately, I was trying to read The Skeptical Chemist yesterday, which is Boyle's most famous work, except it's called The Skeptical Chemist. It's in Old English, and it's pretty hard to understand, at least for me. You almost have to translate it out of the old English form into modern English. And it's much worse than, for example, Newton's optics, which were written in the 1710s or something, which are quite understandable for somebody with with modern English, so to speak. In any case, and I don't know, maybe Boyle was writing backwards to a period earlier than him. But in any case, so anyway, that's the claim about what he said. Now, old Isaac Newton got into the Act 1687. There's a part of the Principia where he talks about gases. It's a little bit obscure. I was just trying to read it yesterday. And in fact, what he's discussing is something very, scientifically fancy, which is, what does a sphere of gas do under mutual gravity? And he knows it's going to be a sphere. He knows that when you have just a big blob of stuff, according to his universal law of gravity, it will all get pulled together, as happens with stars and so on. Anyway, he knew this, but he had to know he wanted to know what a gas was. And what he thought was, it was kind of like the choice number one of Boyle, of kind of the array of corpuscles, and that between them was a force, an inverse with the distance. I didn't do the math yet. Not an inverse square force law, but an inverse 1 over r force law, as opposed to 1 over r squared force law. And apparently, he claimed he could get Boyle's law, pressure times volume equals constant, for a gas from that derivation. Of course, in the end, that derivation turns out to, that whole thing turns out to be nonsense, because what's really causing pressure in a gas is the impact of molecules on the walls of the gas, which is something that it seems that Daniel Bernoulli worked out in maybe 1738. Again, I haven't read his stuff yet. And that's something where, so that was sort of the beginning of kinetic theory. By the way, I'm just moving forwards a little bit into the 1800s. Sort of the big news of that time was steam engines. And obviously steam engines are all about taking heat and making mechanical work, something that people had done. Hero of Alexandria had done a little bit of that kind of thing back in antiquity. And there'd been a kind of a history of trying to, take heat and produce steam, make it push things and so on. But eventually Thomas Newcomen had this sort of practical closed loop system for first using a steam engine to pump water out of mines. And then much later on was James Watt and the sort of fancier steam engine and notions of governors and control systems and things like this. But in any case, the practicality of the steam engine was sort of the big thing of the beginning of the 1800s, and a big contributor to the Industrial Revolution in the end. But something which was the kind of the wow, it's exciting. It's kind of like some people might say about the metaverse today, except in those days it was steam engines. And when you read the marketing material, so to speak, for steam engines, it's really quite amusing because it's so breathlessly, the world is, the future is amazing, and the steam engine is going to transform the world and so on. And it is so amazingly like the marketing material you read about new technologies today. The steam engine did work out, of course. Not all technologies that are breathlessly described work out. But the steam engine, one of the questions was, okay, you're making a steam engine, you've got all these inventions for how you make steam engines. What's the most efficient steam engine you can make? And that was a chap called Sadi Carnot, a French engineer, basically, who had come from this rather political family that was, in favor, out of favor at different times as Napoleon came in and came out and so on, and came back in again. But in any case, Sadi Carnot, 1824, I think, wrote this thing in French. English translation is On the Motive Power of Heat. And he invented this notion of the Carnot cycle, this idea. It's actually fairly interesting, and I need to understand it better. But I think what he really invented was the notion of the abstract machine. I'm not sure that notion had existed before. I think people had the idea of a concrete machine. Now, I'm not sure if this is right, because when we think about clocks, for example, there is an abstract purpose to a clock. When we think about things for like clocks for finding longitude, things like that, there is an abstract purpose to those things. But I think the description of how they work was very much, and there's this cog and there's this cog and so on. Maybe not. I mean, Galileo's last works around 1640 or so were about pendulums. And in a sense, that's sort of an abstract machine as well, because you can kind of describe the pendulum and it's swinging without having to say kind of what the, whether the pendulum has a plant at the end of it, or whether it has a piece of gold or what it is. It doesn't matter. It just is the mass of the pendulum. So maybe Galileo had sort of the precedence on this. But in terms of heat, Carnot was the guy who kind of tried to make an abstract theory of how heat engines would work and those kinds of things. But he didn't really, his work was not widely known at the time. And it really took until the 1850s for things to get picked up and people to start really talking about about the sort of kinetic theory of heat and so on. And I mean, what had happened before that, this phlogiston theory and the notion of caloric and the notion of, in fact, even Carnot still believed in caloric, believed that heat was a substance, like the substance that Galileo talks about, where it's like little corpuscles of fire or something are heat, and they can flow through things, and there's sort of pieces of heat that flow around. Now, a thing, again, I've not really looked at, and maybe I should postpone talking about this until I have, is Fourier, Joseph, whatever he was, Fourier, from 1807 or so, 1804, I think, originally, was the person who started looking at the transmission of heat in materials. Now, it's worth remembering that 1804 is really late in the development of calculus. People like Euler had been around, Gauss was active. Gauss was writing all kinds of fancy things. So there was no lack of fanciness in understanding differential equations, all this kind of thing. What Fourier did was to apply this differential equation technology to heat, which people hadn't really had a kind of a mathematical discussion of. Now, I mean, one of the things that had also made that difficult was, how do you measure heat? Well, you measure temperature. How do you measure temperature? Who's ever measured temperature? Well, Galileo was actually the first person to make a thermometer. He made a thing called a thermoscope, which is something that basically liquid expands and then it comes into it's kind of like people had fountains that were based on this kind of principle of liquid when heated expands and gets pushed up through a tube and then kind of fountains down and so on. there have been examples of this in antiquity, but Galileo kind of tried to make that into kind of an instrument. I think this is now in the 1605-ish time frame, into some kind of instrument that would sort of measure heat, measure temperature. You know, it is funny that I'm pretty sure, I have to look this up, that the Central England temperature time series starts in 1650. So that's the longest running kind of information about temperature and for climate studies and so on that exists. And it didn't start that long. It was less than 50 years after the first idea of a thermometer came into existence. So, but in any case, Galileo kind of began this process of having a measurable concept of temperature. It didn't help that back in the day, I think there were like 35 different scales of temperature that were in use. And that sort of standardized to Fahrenheit and Celsius, and then later Kelvins. But you know, I think that was a bit of a downer in terms of the development of theories of these things. Was, you know, everybody was quoting, you know, temperatures of things in weird different scales. But you know, Fourier, I think, you know, apply math to heat was kind of his thing. And then we get to the 1850s, and maybe I'll talk about that another time, where we really get the development of kinetic theory in the hands of first Rudolf Clausius, and then following soon thereafter, James Clerk Maxwell, William Thomson, later Lord Kelvin. Later on comes Ludwig Boltzmann and also Josiah Willard Gibbs, a US presence in these things. That was more in the 1870s and so on. But it was kind of this really, it took only a modest number of years for this kind of notion of the first law of thermodynamics, law of conservation of energy, which was a Clausius production, and the concept of entropy, which was a Clausius production. Clausius also had a lot of names for things. So he had another name, Ergal was a name that I just learnt, which was his name for potential energy. And entropy was a winner, Ergal was not a winner. Vis viva, the name for kinetic energy, was also not a winner. But Clausius was the person who developed this, you know, entropy is equal to Q over T, dQ over T, ds is equal to dQ over T, and so on. And that was the whole development from there. In any case, this is some history I've been studying. Maybe I'll tell some more of the story another time. I will say that some of the people involved in this, like James Clerk Maxwell, I've become a huge James Clerk Maxwell fan. I think I maybe mentioned that before, but every week now, as I've been studying things related to him, I'm more and more of a fan. He was a very clear writer and very clear thinker. Unfortunately, died at the age of 48, so didn't have as many years to do science as he might have done. And he also wrote about just a wonderful diversity of different topics, and just an interesting chap. And anyway, maybe another time I can talk in more detail about him. Maybe somebody can remind me about that, and I'll probably know more the next time I'm talking about him. All right, let's see. There was a question here from Paul. Did Einstein ever attempt to quantize space-time as opposed to treating it as a continuous medium? The answer is yes. By the way, all these people talking about molecular theories of things, they are, I mean, Maxwell, for example, Maxwell contributed an article to Encyclopedia Britannica. Maxwell was hanging in Scotland at the time, and Encyclopedia Britannica originated in Edinburgh. And he contributed the article about atom to Encyclopedia Britannica, and it's still reproduced in the 1911 one, for example, which is a very famous edition of the Encyclopedia Britannica. And it's very good. It has a very nice historical description. In fact, I was about to go back and check and look at it, because I think it's a better historical description than I found elsewhere about what the Epicureans thought and so on. But anyway, Maxwell talks about the argument between the corpuscularians, the people who believe in discreteness, and the people who believe in a plenum, which was the old name for a continuum. And he talks about the different kinds of evidence that you might get for corpuscular kinds of things versus continuum kinds of things. And it is deeply charming to me that what Maxwell says you could simply translate when he's talking about matter, you could translate it into talking about space, and you would have exactly the things that people told me for years about the fact that beliefs of mine that space and space-time would ultimately turn out to be discrete couldn't be right. And you find the exact same discussion back in the 1800s of people saying, couldn't possibly be right that water is made of discrete things. Couldn't possibly be. It's a plenum. It's not, and people had all these arguments for that. And you know, heat was an interesting case because that was also thought to be a continuum, a plenum kind of thing made of caloric fluid. And you know, heat turned out to be a little bit more of a subtle question. I mean, heat wasn't, and same with what we believe space to be in our model of physics. It's not like, oh, there's just a bucket of space here. It's that it's a more complicated construct that is a continually changing construct that doesn't really have an existence unless it changes. Actually, that's strangely similar to what happens in kinetic theory with the sort of kinetic theory of gases, that gases aren't a thing like a gas unless there's motion in the gas. You know, Heraclitus perhaps was right in this idea that, you know, flow is everywhere, so to speak, that, you know, there isn't really, in fact, it's sort of an interesting point. I hadn't really internalized that before, that in our model of physics, the notion that space is continually changing is critical to the model, because space, there is no notion, except in the center of a black hole where there's a space-like singularity, there is no notion of time having stopped. If time has stopped, there's no observer to observe anything. The universe effectively is not a thing that has extent and so on. And so, in a sense, there is a need for change in the same sense that Heraclitus, I think, perhaps talked about it, although his terminology is very different because he lived 2,000 years earlier, more than 2,500 years earlier, that you know, the possibility of space is a consequence of a sort of a flow in the Heraclitus sense. In this case, sort of the updating of the structure of space through time. So in any case, back to sort of views of space. Well, you know, people, by the time of Einstein, people have firmly thought space was continuous. I mean, Euclid, after all, had assumed that space was continuous by just saying there is geometry. Now, there's an interesting discussion in Maxwell, actually. Maxwell has this in his article in Encyclopedia Britannica. It's a really lovely discussion about the arithmetic versus the geometric view of physics. And what he says is in the arithmetic view, there are numbers, discrete numbers. Now, for some reason, he wasn't internalizing kind of the continuum of numbers as I might have expected him to, because it was certainly known about by that time. That was a little bit before people like Dedekind had really started talking about the formalization and the axiomatization of real numbers, but not too much before that. But in any case, he viewed the sort of arithmetic view of nature as being, there's a bunch of numbers, there's a bunch of corpuscular, distinct, countable things there, versus the geometric view of nature, which was more this plenum, this continuum view that Euclid had kind of pioneered. So he discusses, you know, the atomic view, Maxwell discusses, the atomic view is very much more this arithmetical view of nature. In any case, so, but by the time, you know, for example, Newton has a very geometrical point of view about kind of how things work, and you know, his Principia is very much set up in the style of Euclid's Elements, and it's sort of geometrical derivations of things all the way. So he certainly believed in a sort of a continuum of space in the same sense that Euclid did. And by the time one was, and so the sort of traditions of mechanics that came from Newton and that eventually led to Maxwell's electrodynamics, which is kind of what triggered Einstein to try and work out relativity, and to try and to realize the correspondences between space and time and so on in relativity. That was kind of on the one hand, came out of the mechanics tradition, the calculus tradition, which then turned into the Maxwell's equations for electromagnetism tradition, that then delivered kind of the this notion of space-time that Einstein had, which Minkowski was the one who was really responsible. Hermann Minkowski had been a number theorist and was very big on quadratic forms. And so when he started seeing the distance between 2 points, which in Euclidean space would be, you know, the square root of x squared plus y squared plus z squared, in the Einstein case would be x squared plus y squared plus z squared minus c squared t squared, where c is the speed of light. and t is time. And it's like, that's a quadratic form. Let's just view space and time, the space coordinates, the time coordinate, as being the same kind of thing, so to speak. And that's where this kind of notion of the space-time continuum really came from. I happen to think it was a misleading notion, and because it made space and time seem like too much the same kind of thing, which they're really not. I mean, space is this extent of this hypergraph, and time is the progress of computation by which things are transformed, so to speak, in a very Heraclitean kind of way, I suppose. So I think okay, so Einstein. Einstein did think that space was probably discrete. There's a letter, people have sent me this copy of this letter many times, from 1916, a year after the development of general relativity. Einstein says, I think space is going to be discrete. Also, after he thought about photons, things like that, I think space is going to be discrete. But at this time, we do not have the mathematical apparatus to talk about that kind of thing. And well, maybe he was right. It took 100 more years. It took until we'd understood this whole stack of things about computation and graph theory and discrete math and so on to get to the point where we could really talk about space-time in a sensible way as something discrete. Now, somebody's told me that Einstein actually had another reason for thinking space-time might be discrete. It's a curious reason. Einstein, very early in the development of general relativity, knew that there would be gravitational radiation, knew that just like accelerating charges will radiate electromagnetic radiation, accelerating masses and changing masses will radiate gravitational radiation. And one of the things that had been a big mystery in the theory of the atom was, okay, you've got these electrons, they're being held in these orbits, but an electron that goes around an orbit, it emits radiation, synchrotron radiation, whatever. It radiates. And so that would mean that the electrons should lose energy and they should spiral into the nucleus and go splat. But that didn't happen. And what was realized eventually by Bohr and people like that in the development of quantum theory was the reason that doesn't happen is because the energy levels of the electron are quantized. They're a discrete set of energy levels, and it can't just continuously lose energy and spiral into the nucleus. And so the speculation about what Einstein thought was that he thought there was going to be the same issue with gravitational radiation. Why wouldn't just tiny amounts of gravitational radiation over immense periods of time make every electron spiral into its nucleus? And that's a speculation about why Einstein thought there's got to be a way to show that it's discrete. Now, in terms of this discreteness business, it's sort of an interesting thing to know, how do you show that things are discrete? And there's sort of, in the 1800s, people like Dalton had given sort of circumstantial evidence from the fact that, you know, in water, there's H2O and it's always two hydrogens, one oxygen. That sort of suggests discreteness rather than just there's a bunch of oxygen and a bunch of hydrogen. The fact that there are small integers involved suggests discrete kind of entities, but it had been rather circumstantial. And, you know, as the 1800s kind of chugged along, people tried to get other evidence of discreteness or not, as the case may be. And I think Lord Rayleigh, William Strutt, had one of these where he basically would put a tiny drop of oil on top of the surface of water and see whether lycopodium powder, pollen-like stuff, would fall through the oil into the water, because lycopodium powder gets, you know, pulled in by the polar molecules in the water, sucked in there. But if you put a layer of oil, it can't get through the oil. So the question is, if you put that layer of oil, there's a point at which that drop of oil is spreading out of a region so that it is so thin, it's like, you know, 100 millionth of a meter thick. And at some point, if there is discreteness in the oil, at some point, it will no longer be able to support the lycopodium powder, and that will drop through. And I gather that gave estimates of the size of atoms that weren't totally wrong. And so that should have been giving evidence by the 1880s, maybe, that atoms were a real thing, but I'm not sure how well it was believed. I think Loschmidt was the first person to measure the size of an atom in some way. And I think one way of doing that is using kinetic theory and using viscosity of gases based on sort of how big the balls have to be if they're colliding, so to speak. I haven't yet gotten to that part of my homework, so I can't tell you about the details of that experiment yet. But another very famous one is Brownian motion, which had been observed by Robert Brown, is that his name? Back in like the 1830s or so, that you put these pollen grains in water, you look under a microscope and they seem to be getting kicked around. It seemed like Einstein was the one who first really gave a good theory of that and said, oh, it's discrete molecules kicking the things around. And so that was another sort of, absolute nailing down of there really are molecules. But the question is, finding Brownian motion, finding this idea of a thin layer and knowing that the lycopodium powder drops through or not, I need to find the same kinds of things for the structure of space. And, the clever experiments, and if anybody can figure these out, that'd be terrific. The clever experiments that are just reveal, that see through to the discreteness of space, just like these experiments back in those days, in the late 1800s and so on, saw through to the discreteness of matter. And, one wonders, at that critically spinning black hole, does it just get to the edge where it's kind of like the layer of oil and the lycopodium powder and so on? But I don't know what the lycopodium powder is for the black hole. And I don't know, unfortunately, scientific history does repeat to some extent, but it doesn't precisely repeat. And when one does know the experiment that proves that space is discrete, one will be kind of kicking oneself. Oh, that was really an obvious experiment. That could have been done. I bet that the experiment that shows that space is discrete could have been done, I'm going to guess 50 years before it actually is, when we finally figured out what the correct experiment is. We'll see. It might also be something where you have to really reach to get to the experiment. But, I am very amused as I read about caloric and the substance that is supposed to be heat. And where is it? Oh, it's everywhere. Well, oh, it gets through things. Oh, it does this and that and the other. I'm deeply reminded of dark matter, which is another kind of thing where people say, oh, we don't know where it is. Maybe it's in the Earth's crust. Maybe it's in the center of stars. Maybe it's floating out wherever. We can't quite detect it, but it has an effect. Same thing with caloric. It has an effect. It's hot, but we can't quite detect it. We can't quite put it in a bottle, for example. It has an amusing sort of historical resonance, I would say. We'll see how dark matter turns out. And we'll see whether it turns out to be something that is something about the structure of space-time that is a little bit more bizarre, just like caloric heat is really a property of matter that's a little bit more bizarre than people had thought. It's not, oh, there's just something dissolved in the matter. It's the matter itself is in motion in a way that hadn't been understood before. So, what happened with the quantization of space is Einstein kind of talked about it, said we don't have the tools to study it. By the 1930s, people were quantizing everything. And people did try and quantize space and tried to figure out whether that could work. And they couldn't make it consistent with relativity. They couldn't make something where space is a bunch of little boxes or something that are quantized. But those boxes, when you look at them in different reference frames, you look at them, you're going at 0.8 of the speed of light or something. Those boxes will be distorted, and nobody could figure out sort of a way to make that distortion work in a way that was not that was invariant under relativistic, that was appropriate under relativistic transformations. We finally have such a way. In the causal graphs of our sort of update mechanism for hypergraphs and so on, we have exactly something like that. That is relativistically invariant. It's a discrete model of space-time that's relativistically invariant. But to get to it, you have to go sort of below the notion of space that has normally been thought about. And that wasn't something that was understood before. People had wondered about things like, oh, is space discrete? That's a little bit hard to measure. Is time discrete? That's a little bit easier to measure because there are particles, a whole gaggle of particles discovered around 1960 that decay in 10 to the minus 24 seconds. And people were trying to say, oh, well, maybe, if the discreteness length is 3 times 10 to the minus 5 to 25 seconds, then, oh, we'll see discrete levels of lifetimes for those particles. Those were not observed. But that was sort of an attempt to find discreteness in time in that case. Let's see. Oh boy, sorry, I went on about these things a long time, but somebody's saying they're very interested to hear about the future history of science. Well, I'll have lots to say about second law of thermodynamics soon. for those who really want to watch the paint drying process, I do make these video work logs of what I do every day. And you can see it gradually grow, but it's probably incomprehensible because it's just what I'm computing and so on. It'll get coherent later. You know, I was thinking about sort of the future of things like, you know, caloric and a lot of these things where we say that was a crazy idea, the alchemists, all these kinds of things. And I was thinking to myself, what are things that we think today that will just seem bizarre in the future? And I think one of the things that we're really beginning to understand today is something about the extent to which the small can build up to the very different, so to speak. So, you know, the whole thing that I've studied about simple programs that can do very complicated things, the whole notion that you can have things at a microscopic scale that produce lots of large-scale effect. The whole notion in our physics project, one of the things that was a sort of psychological thing for me to get over in the physics project, or a sort of paradigmatic thing to get over, is that our universe is an unbelievably profligate waster of computation. I didn't really think that. I thought our universe is just computing the way the universe works, but it isn't. It's computing just this unbelievable tree of possibilities, which we conflate together to be the thread of experience that we have. But it's unbelievably wasteful computationally. It's just, you know, gobbling up. It is just running all this computation, most of which just nobody cares about. There's no, you know, no observer to observe it. It just is computing. And what's sort of interesting is as we kind of pull back from this just unbelievably huge amount of computation that's going on, and we see the little things that are floating. It's like the water molecules in the water, and all we see is the eddy on the surface of the water. It's the things that emerge from all that activity underneath. And I think that the realization that there's more activity underneath and a bigger distance to what emerges for us is one of the things that will be something that people say, well, of course, just like after molecules were known, of course, water is made of a bunch of molecules. But if somebody had said that before, when they say, and how many molecules are there in there? There are Avogadro's number of molecules, you know, 10 to the 23, you know, 10 to the 24 molecules. That's just crazy. That's way too many. We say, how many computational operations are there going on in the universe? It's 10 to the 400. Say, that's just crazy. That's just too many. But I think that won't be, those things won't seem crazy in the future. I think that there are a lot of different things that I think will be kind of features of the view of the future. Another one that's sort of an easy one is, you know, this notion that today we have things made of materials. In the future, people would be surprised that everything wasn't made of computers, that it wasn't the case that everything down to the molecular scale was programmable, that we just had dumb materials where we just had a piece of plastic, so to speak, as opposed to a thing that is running computation in its very molecules, so to speak. And, you know, I think that there are, in terms of things about science, I think that this whole, something which is coming very soon is the importance of computational irreducibility and the notion of what might be predictable in science and what might not be predictable in science, what the boundaries of science really are. That's something which, in the next, I don't know, 20, 50, 100 years, people will understand that. And they'll understand that there are things that science can say and predict, and there are things where science just says, well, can't really figure that out. You've got to watch it and see what happens. Because what you can figure out, you could simulate it, but you won't really do any better than just having the thing happen itself. You might be able to have sort of a digital twin of the thing, but you can't have something which is just going to jump ahead and see the answer. So, you know, I think, and there are probably things about the importance of the observer and how that relates to the science that one observes. I saw an interesting letter that Einstein wrote about, which really it's like there are no new ideas under the sun, so to speak. But it was to a person who was an enthusiast of von Frisch's work on bees. And the question, I think, was, you know, bees can sense the polarization of light in the sky. And there was a bunch of question about that. And somebody wrote to Einstein about this. And Einstein was sort of writing about how, well, there might be things that bees or dogs or whatever can sense that we can't. And somehow was talking about the kind of the different physics that might be observable to those kind of critters. And that's very much like the whole story of different points in real space and alien intelligence and so on that I've been talking about recently. So I was interested to see that that was a thing. Let's see. Okay, there's a bunch of questions here. Let me try and Memes is asking, what was the most fantastic experience you had as a physicist? Had a bunch of decent ones when I was a kid. And then I had a great one recently, which was the stuff about our theory of physics. And probably the single most remarkable thing was the realization that general relativity and the Feynman path integral are the same thing, but operating in different kinds of space. That's really kind of, as far as I'm concerned, just a super cool thing. And interestingly, because we were doing this sort of an open science project, probably the very moment where we realized that is actually captured on, somebody actually go back and say, oh, it took these guys a really long time. They had to spend hours and hours talking about this. And then finally it became clear. Back when I was a kid doing physics, I would say the thing I've always liked is when things become much clearer, when there's a sort of a mass of stuff and you manage to boil it down to something very clean, very, very direct. And in the early work that I did on the mixture, this is 1978 or so, on the interface between cosmology and particle physics, there was a lot of hair there, a lot of complicated stuff. And I was pretty pleased to be able to boil it down into this sort of very clean notion of statistical mechanics, general relativity and cosmology and particle physics, actually really using the three big theories of 20th century physics. But being able to make that very clean was something I found really quite neat. But I would say that the thing that has been rather unrewarding, I would say, is you make predictions and then people observe them. And it's kind of like, you think that will be super cool. You make a prediction, you just think it through, and then somebody does the physical experiment, and then they say, well, you were right. But at least in my experiences in particle physics, the story was just much, much muddier than that. There was a prediction I made that disagreed with an experiment that already existed. The experiment was redone. My prediction was right. Not exactly a ticker tape parade, so to speak. It was kind of rather muddy, not the drama that you might think of in a kind of Popperian version of science, where it's like, it's falsifiable. No, it's actually true. We did the experiment. Actual science doesn't work that way. Actual science experiments are hard. You don't know they're right. You need a whole interpretation framework. Sometimes the interpretation framework seeps into the analysis of the experiment. It's a complicated story. It's not a clean, it's not a clean sort of competitive thing where you say, I wager that the world works this way, and somebody says, okay, you win. It's a much more complicated kind of story. Let's see. The question from Mikhail here, what's the history behind migrating the entropy term to information theory? So I think, what happened is that Boltzmann talked about the number of states of a system and said the entropy, which had been defined by Clausius in terms of heat and temperature, he said the entropy is equal to K, a constant now called Boltzmann's constant, log omega, where omega is the number of states. Actually, he called it W. Now, the fact that that's true is basically what's happening is that as soon as you believe equipartition, as soon as you believe that every degree of freedom has an equal average amount of energy, a half kT of energy, for example, where T is temperature, then Q over T is essentially a counting of the number of degrees of freedom, the number of molecules, the number of ways things can twist, whatever else, something that can have energy associated with it. And then the number of states is, let's say you have particles in a box and you have them in discrete little sub-boxes. It's how do you arrange the particles in all the sub-boxes? And that's your omega, and the log of that counts the number of particles. Now, for Boltzmann, that was a complicated thing because he couldn't count particles like that because he didn't know the world was made of particles. People said it's a continuum. But he invented particles. He invented the idea that there would be atoms and that the atoms would be in discrete places in space with discrete velocities. Planck, when he came to think about blackbody radiation and photons, was extremely well aware of Boltzmann's work because Planck was primarily a thermodynamics person, was writing textbooks about thermodynamics and so on. So what Planck really did was to say, actually, that thing that Boltzmann just said was a mathematical fiction is reality. Einstein kind of came behind that, really sort of backing that up. But the thing that, so Boltzmann had this idea of the K log omega thing. And if you sort of take different probabilities for those states for Boltzmann, you get the P log P formula. That is the same formula. So then when Claude Shannon, this is 1940-ish, was studying, this history is muddy, and I don't think it's all understood yet. Claude Shannon, during the Second World War, worked, I think through AT&T, worked on speech encipherment. I mean, Shannon was for a long time at Bell Labs, but he worked on speech encipherment. And meanwhile, Alan Turing in England was working at Bletchley Park on cryptanalysis. And one of Alan Turing's big sort of breakthroughs had to do with understanding better the statistics of codes. And Alan Turing went to visit, the speech encipherment effort and Claude Shannon in early 1940s. I'm not sure exactly which date, in New York City, which is where the Bell Labs was at that time. Nobody knows really what happened there. And it is a remarkable coincidence that Turing's kind of view of the sort of probabilistic way of thinking about encryption would dovetail so closely with Shannon's information theory. I don't know what happened there. I don't know what the sort of traffic in ideas was, whether maybe they were just independently had. But this notion of the number of possibilities, which is a very cryptologically important thing, the number of possible keywords and so on, is something that Turing was really interested for in a very Boltzmann-like way of measuring the log of that, the number of degrees of freedom, the number of independent sort of rotors that you can turn and things like this. Not quite thinking about it that way, but that's sort of what that comes from. And then, so that in any case, by whatever means, Shannon ended up with this idea of sort of the P log P view of entropy. And I think there's a story that John von Neumann said to Shannon when Shannon was talking about this amount of information thing, said, oh, you should talk about it as entropy or minus entropy, because then everybody will sort of just agree with you because nobody really understands entropy. And I don't know if that story is apocryphal or not, but that's and really the interplay between sort of the information theory version of things and the statistical mechanics version has taken a long time to develop. I mean, those were really two very different disciplines. Only with modern quantum information theory have they really merged in any serious way. I mean, there was a lot of obsession with the thermodynamics of computation. Things like von Neumann believed that to do a computation inevitably takes the dissipation of heat. And then Rolf Landauer at IBM was a person who long pushed for that to not be the case. And then Charles Bennett, also at IBM, Charles Bennett had been a molecular dynamics person, and he worked out this idea that you could make a reversible computer. And then Ed Fredkin and other people, and Tom Toffoli and people like that, got into that act as well, somewhat independently. Ed Fredkin, because he wanted to sort of model computationally things in physics, and people like Dick Feynman had told him physics is reversible. You got to have something reversible in computation as well. And so all of those people, and this is now in the 1970s, mid 1970s, were kind of coming up with ways that you could have, instead of having, and of P and Q turn into a single bit, which is not reversible, because from that single bit you can't deduce what the two inputs were, of having a 2-to-2 gate. And these are what get used in quantum information systems all the time now. But that was sort of a place where sort of the informational thing started mixing with statistical mechanics, but didn't really happen in a serious way, I would say, until the 90s or later. Let's see. Should go soon here, but well, all kinds of interesting comments here. Parker is asking, what's the process like making computations for the thermodynamics project? There haven't been very elaborate calculations mostly. The computations, the fanciest one has to do with computing the entropy of space-time in a toy version, and that's taken a few weeks of CPU time. But it's not, we've not been as extreme as some of the other things we've done. Well, let's see. Maybe I can tackle one more thing here. A lot of interesting questions here, which I know would take me too long to talk about. Okay, Satoshi here is asking, what do you think about engineering efforts that help discovering science, building tools and experiments? I've met many scientists who dismiss engineering as less intellectual. Look, here's the story both of my life and of the history of science, which is it's a cycle between the development of technology and the development of basic science. Technology develops tools that let you see a new thing in basic science, and the basic science eventually lets you develop the tools that give you technology and so on. And in my own life, I've done this cycle maybe 5 or 6 times of going from tool development to then enabling certain development of some basic science, then realizing that that basic science can be used to build another generation of tools and so on. That is the history of science. I mean, that has been for, well, certainly solidly 500 years, and arguably much longer than that. The story of the history of science is this alternation between the development of tools and the development of the kind of pure abstraction of basic science. Now, the way that scientific communities work is something where people say, look, the only thing that matters is this particular devotional activity, so to speak, is this particular kind of thing that we do. And everything else is irrelevant. Now, I noticed that even when it comes to, I don't know, making, this is the thing where the paradigm you have, the way of thinking you have, determines what you think matters and everything else doesn't. I mean, to give a very mundane and trivial example, I'm going through some of my own archives, and there's places where we scan documents, and there was a FedEx envelope, very early FedEx envelope, actually, from the early 1980s. Looked amazingly similar to a FedEx envelope today, but in any case, a FedEx envelope where the content had been scanned, but the person who was doing the scanning, why would anybody care about the envelope? That's not the point. Well, it turned out it was the point for me, because the envelope had an air bill, which had a date, which allowed me to date when certain documents had been produced and so on. But so it's the same thing for a lot of stuff people study is, without a framework, you don't know what to study. But also, there's a question of sort of what matters. So in a study, like a good example in mathematics right now, is people they write down theorems, they write papers with lots of theorems, and maybe there have been 4 million theorems written down in the history of human mathematics. But the question of what the statistical properties of that whole gas of theorems really is Well, nobody studied that. That's this field of empirical metamathematics that I've done a little bit on. But that's something where nobody would really care. I mean, it's like, oh, there's a whole bunch of theorems over in this direction. I don't care that there are more theorems there than there are there. Well, until there's a theory that allows you to say something on the basis of that. Now, so what tends to happen is within a field of science, and it happens even within a specific field of science, it's like all that matters is the thing that is defined to matter by that field of science. Now, a good example, actually, let's take machine learning as an example. There were people who wrote papers about machine learning for, well, back to the 1940s for sure. And mostly, these are pretty unreadable, mostly. They're very engineering kinds of things. Oh, you can do this hack that does this and does that. Well, now, of course, last decade, machine learning is all the rage. Although most of what is really being done in machine learning is, look at this engineering thing we did, it produces these results. There isn't really a basic intellectual theory of machine learning. There are ideas, and there are ideas that give intuition for engineering, but there isn't really a sort of a theoretical framework like that. And it's sort of interesting to see that there are sort of not academizable aspects. In fact, when fields go through this phase of becoming academic, it's sort of an interesting thing. I mean, it's like, the trades, all kinds of different trades, from, blacksmiths to I don't know, carpenters to whatever else. There are things to know in all of those fields, but they're not really academic things to know. I don't think people, I mean, they probably do now, but, write papers about carpentry. It's not a field like that. Even when you invent some new kind of, wood join or something, I don't think people write, I'm sure they do now, write academic papers, but that's not the primary way in which knowledge is communicated, is not this kind of academy type based communication of knowledge. And I think in a lot of these areas of engineering, I mean, like take software engineering, for example. People will teach courses about software engineering. Some are sensible, some are a complete waste of time, because really software engineering is mostly about sort of, it's not a story of facts. It's a story of skills and experience and actually doing it and knowing yourself and knowing how you do certain kinds of things and so on. And it's not something where, memorize these facts about software engineering isn't really, I'm sure, I'm horrified to imagine there probably are. Well, okay, here's an example of something that is not academized yet, is language design. Thing that I've spent much of my life doing is the process of sort of constructing the functional design of a computational language. It's not, I don't know if there are, nobody ever showed me any academic papers about those things. Maybe people have studied things I've done, maybe not, I don't know. I know people have used some of the things we do on our live streams doing software design as things for software engineering classes, but that's a little bit of a different thing. But there is a body of knowledge, and certainly within our organization, we've developed quite a body of knowledge about sort of how to do computational language design. But it's not something for which there is an academic kind of published papers type structure. Same with most of software engineering. I mean, and sometimes these fields, even things one has built at an engineering level, one looks years later, and people have kind of made a course out of doing something like that. And you realize that the real meat of the software engineering is, other than just saying, well, it becomes like a history course. It's like, this is what happened. This is what these people did. Not, this is the generalized version of that. I suppose the generalized, history is about sort of what happened and so on. And I suppose one could ask, is there a similar kind of course about how to change history? Well, if you're in a military academy, maybe, or if you're doing, some kind of political thing or some management thing, maybe there is. But it's kind of there's what has been done, which is very academizable, and there's, the kind of the artisanal work of what you do next. And in any case, so I mean, there are these fields where there's very academic traditions, and there are the ones where there are not. And it is, and in academia, for example, I don't know, if you write a program that's used by 1 million people and you write a paper that's read by 5 people, it could be the case that for your tenure review, the paper is what matters, the program nobody cares about. That's a feature of, it depends what you care about. It depends what you think matters. Is it the contents of the FedEx envelope, or is it the envelope itself type thing? Whatever. I mean, it's the same thing that happens with people who are involved with collecting systematic data in different kinds of fields. They usually, in many fields, they have low kudos in that field. In some fields, they're the king of the hill. In some fields where I think, for example, in bioinformatics, maybe that's not quite happened that way, but there are fields where the aggregation of large amounts of data is the most dramatic thing that's going on, and the people who are doing it are kind of the top dogs. And there are other fields where it's like, oh yeah, there are those people in the back room who collect data in our field, and they're just staff scientists, and they're the people who are hangers-on at the universities, and we don't care about them. And the people we really care about are the professors who are publishing papers. Now, is that the right attitude? No. I mean, it's, but this is what happens in kind of developed fields where there's a lot of stratification and specialization in the different roles. And, academia has a particular specialization in this particular workflow of write about something that you can write a paper about. Well, you may develop a piece of software that's unbelievably useful, but writing a paper about it, what would you say? I mean, it's kind of funny. I realized recently I wrote some things about the development of SMP, the precursor of Wolfram language and Mathematica. And I realized I'm not sure people wrote about software development. I mean, I wrote about kind of the conceptual design of the system, a little bit, not too much, but sort of intellectualizing something which I think is often just a pure, artisanal kind of activity. So it is an interesting point that, if you ask the question, well, just to give an example, when computer science became really popular in the 80s and 90s, and universities, realized, oh my gosh, we have all these students who want to study computer science, we don't have any professors to teach it. There was this kind of big pull to get practitioners in to be professors, people who had been software engineers, out in the field, so to speak, doing stuff. And it's like, okay, now can you teach this? Well, a lot of what that led to was more kind of trades teaching, so to speak, of, I've written programs, I'll teach you how to write programs too. It didn't really intellectualize that much, but there was sort of and perhaps that's that's been, and I don't know, it's an interesting question, how much intellectualization of, so for example, teaching software engineering should there be? Because it's like, if you teach somebody a language, French, English writing, how much should you just teach, this is what you do, this is what the words are, and how much should you start saying, and this is how you can diagram your sentence and see that, to boldly go is a split infinitive, which you can see, in the parse tree has, a verb phrase that has an adverb stuck in the middle, as opposed to an adverb as a pre-verb or whatever it is, who knows? In other words, how much do you teach just the doing, and how much do you try to teach the theory of the doing? And is there even a credible theory of the doing? And is it in fact the case that people find it useful, who are learning something, find it useful? One of the things I've noticed is that in teaching Wolfram language, for example, I have noticed, and I haven't done very much of this recently, but I did a bunch of experiments a number of years ago with kids. My efforts with kids these days seem to be talking about things more general than the specifics of programming. But the things that I noticed is that if you try and teach the theory first, for almost all kids, that's a hopeless proposition. The only kids for whom it is not, is my theory is, those are the kids that will grow up to be pure mathematicians and things like that. There are some people whose turn of mind is, just give me the structure. It can be as abstract as you want, and then I'll fill things into that structure. For most of us, including myself, for example, it's like, just show me some examples of how things work so I get an intuition for what's going on. And once I've seen some examples, then I can kind of build up this abstraction layer on top of that, and then I'll understand the abstraction layer. But I think that's, again, with respect to the teaching of things and the what matters question, the abstraction can be very austere and very incomprehensible without kind of the actual examples. And so when you try and take something that is essentially an engineering type of thing, and you try and say, and now I want to abstractify it, you'll end up with this incredibly austere and incomprehensible abstractified version of it that may or may not be useful. Sometimes what happens is that you go sort of up to the abstraction and then back down again to the practicality. And I mean, certainly in my own life, that's an activity that I've done many times, is you take the big blobby mess, you drill down, you find those primitives, often very abstract primitives, that are underneath the big blobby mess, and then you build back up again, and then you realize it isn't so big and blobby after all. There's actually ways you can structure it and ways you can make a lot of progress in understanding what's going on and building useful things from it. And that's been, for me personally, that's been very much my personal sort of discovery and invention workflow. So, but I think it's a fair observation that this sort of downgrading of the tool builders, at least by the quotes intellectuals. I mean, to be clear, tool building is a deeply intellectual activity, just a little different from the kind of intellectual activity that is the things that people write academic papers about. I mean, I would say that, for example, the language design process is, I worked on a bunch of intellectually fairly demanding things. That is probably the single most uniformly intellectually demanding thing that I've ever tried to do. And I've been doing it now for 40 years. So I've developed some ability to do it by this point. I noticed this from memes. Computational language design is being a modern day wizard. Yeah, you're defining, well, people don't yet understand the importance of it. I mean, one day people will understand, because it is the framework that defines how one thinks about things. And that's kind of the most upstream kind of thing in intellectual work, is to define the framework for thinking about things. And it's a very general, kind of very broad way of doing that. In talking about modern times wizardry, one of my kids had a computer disaster day before yesterday, and I was talking to them on the phone about a computer that just refused to charge from the power outlets and so on. And I'm realizing, I'm looking up, how do you reset the what is it called? Memory controller, I think, on a Mac, the SMC thing on a Mac. How do you reset the non-volatile RAM and things like this? And it's just crazy, because the things you do, you hold down 3 keys and then you press another key for 7 seconds, and you're doing these other things, you're letting things up. This is, if somebody said, what do the shamans do? What do the what do the kind of incantations of old by the wizards and witches and so on, what were those all about? It's like, just see the modern engineering design of computers and their boot sequences and things, and that is sort of the modern version of this. And it really is quite a strange thing. I mean, it's kind of like an incomprehensible thing, that holding down that combination of keys while the thing is booting, when it's doing this for some number of seconds, it's kind of, I just find it interesting that there are these processes and phenomena that are just sort of have arisen many times in the history in human history, and that they have such similarity, and that they're now obviously there is a certain resonance of, we know it was done that way historically, but there's also a certain resonance of, we're still humans, and we still sort of are biologically very much the same as we were 100,000, 200,000 years ago. And so there are certain things that sort of are natural to us based on our biology, so to speak. Anyway, I don't know I'm not sure I can quite tie it all the way from the weird key combinations for booting Macs in safe mode or something, and versus the incantations of when you have this big cauldron that you're pouring things into. All right, I think let's go into here. Gosh, so many interesting things. This is always a fun conversation. I wish it was more. Wish it could be even more interactive, but we don't really have a good mechanism for that. Zayden is commenting: technology, science, social relations all co-evolve. Yeah, I think that's true. I mean, I think that it's also another thing that you see a lot in the history of science is the pre-discovery. Somebody discovered something and they were ignored, and I've certainly seen that in my own life of things I've discovered and nobody paid attention to it, for a long time. And then I think what happens is there's an encroaching of kind of socially understood stuff that eventually encroaches close enough you can kind of tunnel through the barrier, and then sort of there's general understanding of what of the core thing that was discovered, and sometimes that takes 100 years or more for the kind of the general understanding, sort of the bubbling understanding, to get close enough that you can kind of see through that the new thing is kind of reachable from that socialized understanding, so to speak. And when it isn't reachable, it's kind of like, well, I could start just making up English words and saying them, and nobody would understand them. And it's like until those words have become a little bit familiar. What was a word that I just saw recently? Well, I saw a word recently which Francis Bacon used. Gosh, what was it? Quiescence or something? I'm not sure, but it meant the essence of something somehow. At least by context, that's what it must have meant. But in any case, I mean, there are words that sort of, just about make it into, well, like the word chain, for example, okay? We sort of might think we know what a chain means, but then there's blockchain. And then there's a completely new kind of meaning of the word chain. When you hear chain in certain kinds of settings, you have a completely different cognitive framework now than you might have done, 20 years ago. That's an example of sort of the encroachment of sort of ambient ideas onto the ability to explain a particular thing. All right, I need to go here, but thanks for joining me, and maybe I'll have done more of my homework by next time and be able to tell you more about the history of thermodynamics and things like that. But until then, well, bye for now.